In this video then we're going to look at simplifying surds, and we're going to assume a couple of things. In basic simplification of surds, you learn about the fact that you can do something like this. So if you have, let's say, a constant a plus another constant, a scalar here, and then you have this square root of a surd, so b, that what you can do with b if that number gets larger, so say that number is, I don't know, 50, so let's give an example of 1 plus, let's just have k as 1 plus square root of 50. So this is an example. 1 plus the square root of 50, you can split that apart. So you can have something like, well, you would have 1 plus the 50 becomes 2 times 25, so 2 times 25. And that 25 there can also be split apart, so let's just write 1 plus, well, not so much split apart, I suppose, as the radical sign itself gets split, so like this. So we have just a short radical sign there times root 25, so we can happily do this. And then of course root 25 is just 5, so we've now got 1 plus, well, 5 times root 2, so 5 root 2. And this whole process here, where we're splitting apart, recombining, and so on, is called simplification. So this is how we simplify surds and get them into this basic form. If they've become a bit kind of knotty, a bit kind of complex, we simplify them down to that basic form, a plus k root b. So we've looked at that in previous videos. We're going to now do something a bit more advanced, which takes these ideas to a kind of new level and looks at more complex problems. So problems like this, let's have a look at something like, well, take any surd. We'll now leave off this constant here and just work with that constant a being 0. So we just work with square roots, or roots. So let's have root 5 plus root 6, for example. So a combined surd is when it gets more complex. Now, if we have a combined surd like this, then what we can do is multiply out with another combined surd, and something very interesting happens. So let's have, I don't know, root 3, let's have minus root 6, so another combined surd, but we've got this root 6 which is common, so let's see what happens when we do that. Now, what we're doing, of course, here is foiling, just as we did when this was just a constant. I tend to use the first and the last, because that's sometimes with surds works out nicer. So instead of foiling, F-O-I-L, I do first and last, and then I do outer and inner. But you can do it any order you want, of course. So first, well, we've got root 5 times root 3. So we've got root 5 times root 3, and looking at this kind of idea, we can now combine, so we can immediately write that as root 15. So that becomes root 15. We've now got the last, so we've got root 6 times minus root 6, so negative root 6. Well, that's going to be negative root 36, which is simply, well, let's just write it down, negative root 36, which of course is going to simplify to just 6. So the square root of 36 is 6, so it's going to be minus 6. But let's do the rest. So the outer and inner now, we've got minus root 30, so root 5 times root 6 minus root 30. And we've got the inner, which is root 6 times root 3, which is going to be plus root 18. Okay, now when we get to this stage, again, we're looking for something like this where we can simplify. We also might have the same situation here, or here, or here, where we've got a square in there that we can pull out to make a surdic quantity like this. So we're just always trying to get as small a number as possible under the radical sign. In this example, in fact, the only possibility is this one here, the 36. So we're going to end up with no constants, so we'd start with a constant if we had any. Now we're going to look at our numbers. So we've got, well, we'll start with the constant, sorry. We have got a constant, we've got minus 6, so root 36 is minus 6. Now we're looking along here, well, no, we can't do anything with 15, we can't do anything with 30, we can't do anything with the 18. So we've got plus root 15 minus root 30 plus root 18, and we're done. And so very often with surdic simplifications like this, using surds, we end up with this long string, because so many of these integers, when we put a square root over them, can't be simplified any further. And in part B, in fact, we'll look at why this is the case, and why surds have this particular kind of flavour of this long string of numbers. Okay, now an important second sort of prelim, if you like, is the idea of a conjugate. And so if I take these numbers again, so root 5 plus root 6, and multiply this time by the same numbers, root 5 plus root 6, but change the sign in the middle, so it's root 5 minus root 6, then this second bracket here is called the conjugate of the first. So why do we do that, and why is that an important idea? Well, if I now do the same operation, so first and last, so root 5 times root 5, that becomes then just an ordinary number. So root 5 times root 5 is root 5 squared. Root 5 squared, of course, is 5, so we got 5. And the last, root 6 times negative root 6, we've already seen that that is going to be negative 6. So negative 6. So that's the first bit. Now, second bit is when I do my outer and inner. So to start with my outer, outer is going to be root 30. And my inner is going to be positive root 30. So the conjugate produces this idea of cancellation. So because I've got a negative value and exactly the same positive value, these two cancel each other out. So we're just left with this bit here. And that's very important when we're trying to rationalize a denominator, which is something we saw in an earlier video. Okay, now if all this is coming a bit rushed, do go back and check previous videos to make sure you understand all of this. But basically what I've done now is I've run through, so 5 minus 6 minus 1, I've run through the basic ideas that we're going to use in this video for more advanced questions. Now, what kind of question can we answer using these ideas? There's two that I'm going to look at, and they always involve fractions. So here we've got, in other words, both a numerator and a denominator. So here, if we again take these sorts of numbers, so let's think root 5 plus, let's have a combined surd here, 2 root 3. So 2 root 3. And we'll choose as our denominator root 10 minus root 6. Minus root 6. Okay. Now, immediately what I want to do is sort this top out a little bit. It's often a good idea to bring that 2 back underneath, just so that you get a simpler sort of term in here, even though it would simplify. So in other words, what I want to do is make the top root 5 plus, well, 2 is going to become, under the root sign, going to become 4. So it'd be 4 times 3, so it'd be root 5 plus root 12. Okay, so root 12 would simplify to 2 root 3. But there we go, we're putting it all under the root sign now, the radical. And underneath we've got our root 10 minus root 6. Now, we always want to rationalize the denominator, so what I'm going to do immediately is put that in brackets and write it out again using the conjugate form. Whoops, not times, plus. So instead of the negative, instead of minus, I'm using now plus root 6, and then just extend this fraction bar here, So again, at the top, we've got root 10 plus root 6. And of course, what I'm doing here is using this idea of the conjugate. I'm not changing this form at all, but I've got one quantity over another quantity, which would cancel out. But I'm using this as a way of removing the surds from the denominator. And that's called rationalising. So now what we do again is FOIL it. So let's FOIL the numerator first. So we've got root 5 times root 10, which is going to give us root 50. So root 50 is our first term. Our last is going to be root 6 times 12, so 72. So root 72. And now our inner and outer. Well, we've got our inner is going to be root 120. And our outer is going to be root 30, so plus root 30. Okay, so that's our numerator done. I just draw my fraction bar here. Okay. Now, what we should find in our denominator is a bit of this cancellation that we looked at up here. So first of all, root 10 times root 10 is going to give us just 10. So if I write 10 here. And then we've got, so that's our first. Our last is root 6 times root 6, so negative root 6 times root 6 is going to give us 6, so minus 6. Now, just to check, our root 10, so outer and inner, so outer would be root 60. Take away our inner, which would be also root 60, so that just cancels out. So I end up with, let me just erase for brevity. So 10 minus 6, we end up with a denominator simply of 4. So there we are. We've rationalised our denominator. And is there anything else we can do? Well, yes, there is. Because if we look at some of these values here, they will simplify, if I just tick the ones that will. So our root 50, well, we're looking for a square in here, and 25 is very often the one that comes up as being something that we can use. So 25 we're going to be able to pull out of there to just give us 5. And 72 looks a likely fella. 4, definitely. But actually 36, the square of 6, 36. So we're going to be able to pull 6 out. So that one is going to go. This one here, 120, let me think. Well, 4, because half of 120 is 60, then half of that 30. But if I go above 4 to think of 5 squared, so that's not, sorry, 4, 16 won't work, 25 won't work, 36 no. So we're done. The only thing we can get out of that is 4, but that 4 is worth taking out. And 30, it's a good one to learn actually. 30 doesn't have anything that we can remove, so no 4s. 16s, etc. So that one will not simplify. Okay. So now to complete our simplification, we are pulling out 25 here, so that will give us 5 root. So 2 times 25 gives us 50, so 5 root 2 equals root 50. Here we're pulling out 36, so that's going to be 6. And 2 times 36, so it's 6 root 2. Here we're pulling out 4, so that's going to be 4, so 2 on the outside, and it's 4 times 30, so 2 root 30. And here we've got, what have we got? Just root 30, so we've got root 30 as our final term here. All of this over 4, so we draw our fraction bar here. 4 gives us as our numerator, well, we've got here 5 root 2 and 6 root 2, so that would be 11 root 2. So we're looking at like terms here. The other like term is the 30, the root 30s, so we've got 2 root 30s here, and another root 30 gives us 3 root 30. 3 root 30. All of that divided by 4 and there's our simplified surdic quantity. Okay, so that's probably at GCSE as complex as any problem's going to get, but just to finish this video, what we're going to look at is an even more complex situation, because that will give us some practice as well, and you might be curious anyway to know what happens if our terms go from 2 to 3 now. So let's have a look at, and because you'll see how complex this gets, I'm going to keep this as simple as possible. So let's have a constant of 2, then I'll only have to double. 2 minus 2 root 2, 2 root 2, plus, let's say, root 5. So we've got 5s and 2s, that should work out quite nicely. And I'm going to keep it pretty much the same underneath as well. So in the denominator we'll have 2 minus, this time just root 2, minus root 5. So there we go. There's our problem that we're going to simplify, our numerator to denominator. It does need simplifying because we don't want any surdic quantities in the denominator. We've got quite a complex surdic quantity now in that denominator, which we're going to try and remove. So the idea here is, although the numerator might stay quite complex, the name of the game, the prize if you like, is we will remove the all trace of surds from the denominator, because that's what we do when we simplify. Okay, so let's now rewrite this. So if we've got 2 minus 2 root 2 plus 5 to start with, underneath here then we're going to have the same, but what we're going to do is find the conjugate, so that we can begin removing the surds from the denominator. So if I put that in brackets, what's the conjugate of this 3-term surdic quantity? Well, it takes a little bit of thinking about, so I'm going to just go to one side and think about this a little. If I bracket off this quantity here, then what I would need to do is change the sign here, because this is 2 minus root 2, but this would be a plus now because that minus 1 is distributed throughout that bracket. So if I just change the colour of my pen here, if I put brackets in there now, I haven't changed anything, but I've got 2 minus root 2 minus root 5. So in the brackets I've got root 2 plus root 5. Now that's very important, because what I've done by bracketing this out, again if I change colour you'll see what's going on, is I've created a quantity here which I can think of in terms of x. So in other words, I've got 2 minus x equals root 2 plus root 5, so 2 minus x here. And what I'm asking is, what is the conjugate of that? Well, the conjugate of that I would multiply out so that I would remove my surd, the conjugate is going to be 2 plus x. Okay. So now thinking about that, I'm going back to this problem. Let's in fact just remove those brown brackets here. Okay, and just put in ordinary brackets. You can use square brackets here, but doubling your brackets doesn't tend to get too complicated. Now, so what I'm going to do is extend my fraction bar here, just as we did before. Put my second term, my conjugate term, in here, and just work it through carefully. So 2, instead of minus, plus, and then my x is going to be root 2 plus root 5, and close brackets. So there I've done my denominator. I've got my my first term in the denominator, but I've got my second set of brackets here, which are now the conjugate of the first. Okay, So I must do the same to the top, so I'm going to put all of this in brackets now. That should be a 5, so let's make that pretty clear. Again in brackets, 2 plus, now I won't need to have these in brackets anymore, so just removing the brackets, root 2 plus root 5, like that. Okay, so that rather complex operation was necessary to do the next bit, which is just computation really. It's just working through now until we see what happens. We simplify the numerator and the denominator. Okay, let's do it. So the task here is to multiply through 3 times. So to show you how that works, what I'll do I think is just start with that 2 and remind us what we're doing here. So we've got a 2 that we're multiplying all 3 of these terms here. You can't use a grid system here, interestingly, when you've got 3 terms. It would be a cube, I guess. So what you have to do is just work very, very carefully. So that 2 is going to multiply that 2, then it's going to multiply that root 2, and then it's going to multiply that root 5. Okay. So 2 times all of this, in other words. So we're going to have 2 times 2 is 4. Nice and easy. 2 times root 2, well that's 2 root 2. Now what have we got? 2 times root 5, well that's 2 root 5. And that's the first term multiplied through that second bracket. So now what we've got to do, if I choose a different colour, just so you can see what's going on, I'm going to work with this second term now, which is in fact negative 2 root 2. So that's important. Negative 2 root 2. And again, multiplying through all of this second bracket. So 3 terms there. So negative 2 root 2 times 2, well that's going to be negative 4 root 2. So negative 4 root 2. Negative 2 root 2 times root 2, well that's going to be negative 2 times 4, so that's going to be negative 4. And negative 2 times root 10, so negative 2, okay, there we go, times root 10. Okay, so I hope that's clear. Let's just keep it nice and clear in case it's so easy with these problems to get muddled, so let's just keep it nice and neat and go fairly steadily. Now third term, let's use blue here so you can see. So third term here, and again it's root 5 multiplying through all of this second bracket here. Okay. So root 5 times 2, well that's going to be 2 root 5, so plus 2 root 5. Root 2 times root 5, well that's going to be root 10. And we've got root 5 times root 5, so we've got plus 5. Plus 5. And we're done. That long string there is when we've multiplied out those 2 brackets in the numerator, and it's nice to get that done. So let's now draw our fraction bar. Okay. Nice long fraction bar. And now what we should have is an easier time on the denominator, because again we've got this conjugate idea which eliminates the what in algebra you call the middle terms. So we just need to worry about the first and last. So it's 2 times 2, which is going to be 4. 2 times 2 is 4. Minus, well, our last terms are going to be another set of brackets to multiply out. So we're going to do first and last first. So we've got, if I put brackets here, root 2 times root 2, well that's going to be just 2. And our last is root 5 times root 5. So root 5 times root 5 is just 5, so plus 5. And what we've got now is our inner and outer. So if I do my outer first, it's going to be root 2 times root 5. Well, that's root 10. And our inner is going to be root 5 times root 2 as well. So that's 2 root 10. So we say plus 2 root 10. So what have we got? We can simplify the top, we can simplify the bottom. So if we rewrite this, what I'm going to do is look then for like terms. First of all, I'm going to look for these constants. So if I again use a different color, let's use purple this time, just so that you can see what's going on. I'm looking for all the constants in that top row. So I've got a 4 and a minus 4, so there's a minus 4 there. I'm working through, at the end I've got a 5, so it's 4 minus 4, so that's 0, plus 5 gives me 5, so 5. And now I'm looking for, well, let's just look for our root 2, so root 2, a root 2 there, and that's all the root 2, so I've got 2 root 2 minus 4 root 2 is minus 2 root 2. Okay, now let's look for our root 5s. Again, I think there's just a couple. There's a root 5 there and a root 5 there. So I've got 2 root 5 plus 2 root 5. That's going to be 4 root 5. And I do think it's a good idea to tick them as you're going along, because then at the end of this operation we can make sure we haven't missed anything out. Okay, so finally our root 10s, so we've got a root 10 there and a root 10 there. We haven't missed anything out, have we? No. So our root 10s then, 2 root 10s here, we've got negative 2 root 10 plus root 10, so it's going to be minus root 10. And that's simplified the top. Okay, now let's draw our fraction bar again. So we've got 4 minus 2 minus 5, or if you like 2 plus 5 in the bracket, so 4 minus 7. So we're going to have 3 in our denominator, minus 2 root 10. So we've got 4 minus 7 is 3 minus 2 root 10, minus 2 root 10. So that's remove the brackets in the bottom. So that's an interesting stage to get to. Certainly what we've done is simplified this denominator here. So we've sort of halved the number of surds that we've got in there, but we've still got a surd in our denominator. So we're only halfway through the problem. What we've got to do now, I'm going to actually factorize out. So if I just repeat this, 5 minus 2 root 2 5 minus root 10. What I'm going to do is I'm going to factor out minus 1. And you'll see in a moment why that's a useful thing. So if I say minus 1, I can put everything in brackets. Then I've just rewritten that. So I get a nice bracket in here instead of something complex. Now, final stage then is to do the same sort of thing that we did up here, in fact, and what we did in the arithmetic surds video, which is to take the conjugate of this now. So in the numerator, I'm going to have 5 minus 2 root 2 plus 4 root 5 minus root 10. My fraction bar underneath. It's a bit difficult to draw when you're this far down on the graphics tablet, but hopefully that's clear enough. Now, what I can do here, because I've factorised that out, I've just got 3 plus 2 root 10, so my conjugate is going to be 3 minus 2 root 10. Like that. So if my conjugate is 3 minus 2 root 10, that has to go in the numerator as well. minus 2 root 10. And what I suggest you do at this stage of the video is have a go at that. You know, if you're not used to these kind of operations, what I did up here is very useful practice. And instead of taking you through that, which we've already done, I'm going to just jump a step here now, multiply that out as a long string, simplify it, and you would get this. So we would get 35 minus 46 root 2. So all the root 2's gathered together come to negative 46 root 2. All the root 5's come to 20. So 20 root 5. And all the root 10's come to 13 root 10. So just skipping a step there in the interests of time so this video doesn't become too long, but that's the numerator multiplied out and then gathering like terms. Okay, the really interesting bit comes with the denominator, so let's do that. So again, drawing my fraction bar. So now we've got, well, let's just put our negative sign here and do everything in the brackets. So we've got first and last terms, so we've got 3 times 3, well that's going to be 9. We've got 2 root 2 times minus 2 root 10 times minus 2 root 10 is going to give us minus 4 root 10. There we go. Minus 4 root 10. Sorry, not minus 4 root 10. I thought I'd made a mistake there. There we go. Root 10 times root 10 obviously is 10, so minus 40. Okay. Minus 40. And if you think about the inner and outer, you've got the 3 times negative, so you've got negative 6 root 10, and here you've got positive 6 root 10, so that's the inner and outer will cancel out in that way. Okay, now finally what we can do is just sort this out. So if we've got, let's have a look here, if we've got minus 9, let's rewrite it actually. So we've got final line 35 minus our 46 root 2's plus our 20 root 5's minus our 13 root 10's there. So that's our top line, done. What we need now is a whole number in the denominator. Let's complete our fraction bar there. So minus 1 times 9, well that's going to be minus 9, and minus times a minus gives a plus, so we've got 40 minus 9, so our denominator is going to be 31. And there we have it. Okay, now just to reflect really on the nature or the properties of surds, I've just laid out some Cuisenaire rods here. Now the Cuisenaire rods of course are used not just in primary education but also with older students, and they represent, I guess, the first numbers that we learn, which are the natural numbers 1 to 10 here. But in a way, learning this doesn't prepare us for working with surds, because what we're used to is 1 plus 2 plus 3 plus 4 plus 5, let's say plus 6, all combining together and becoming a single number, 21. Now with surds, as we've seen, this can't be done. In fact, that's what defines a surd. So where if we were to, let's say we square rooted everything, the square root of 1 is 1, so that's not a surd. But if we added now the square root of 2, 3, 4, 5 and 6, so square root of 2, 3, 4, 5, and 6, then you can see that the only two numbers here that are going to reduce down, we're going to simplify, are the ones that become integers. So we end up with 1 plus square root of 4 is 2, so we end up with 3. So we say this equals 3 plus, well, just this string again. So we always end up with these strings which won't easily reduce. 5 plus 6. So I guess that's why we tend to get these strings. I guess that's why it feels kind of hard and frustrating, because we can't just simply get it down to one number. But that's the property of surds that we're working with. And it's interesting to think about these Cuisenaire rods, because what surds obviously have a lot to do with is squares. So let's just think about what we can and can't represent with Cuisenaire rods. So we can represent the square root of 4 here. So we've got 2 add 2 is 4. So this represents 4 as an area, a square area. And then if we've got a square area, we know that one of the sides is the square root of the area, which gives us the side length of 2. Let's have a look at another one. If we have 3, add 3, add 3, we end up with 9. And of course the square root of 9 is, again, an integer, whole number, 3. But what the Cuisenaire rods can't do is they can't represent the square root of, well, let's choose the in-between values. So we cannot represent with the Cuisenaire rods the square root of 5, the square root of 6, the square root of 7, or the square root of 8. Although, I guess we could begin to represent the square root of 8, because this, as we've seen, simplifies to the square root of 2, so it equals the square root of 2 times the square root of 4, and so we have 4 root 2s. 2 root 2s, because the square root of 4 is 2, so that equals 2 root 2. But again, we can't represent root 2 using the Cuisenaire rods, which is precisely why it's represented as a surd. We leave it though under the surd form, so it's in exact form. So you might want to do some further investigations to look at this, these properties of surds and the nature of surds, and just to get used to what's going on here. If, for example, we laid out 16, and so we've got square root of 16 is 4 here. What can't we represent? Well, we've got square root of 10, square root of 11, root 12, root 13, and root 14, and root 15, I guess. But let's just look at this string here that we've laid out. Well, again, this won't reduce down, this won't reduce down, and only this one, square root of 15, wouldn't actually. So 13, whoops, I see, I've made a mistake. I do apologise. So there we go, 14, 15. I thought I had enough room. There we go, 14, 15. So it's only this one that will simplify. Equals, well, what have we got? 4 times 3, so it's the square root of 4 times the square root of 3 equals 2 root 3. So that one we can reduce down, we can get an integer out, but it still is a surd. And so we get used to this idea of surds not reducing down. And one thing that's really important, and that's a misconception, a problem that we mustn't fall into, is that when we get two surds, like root 2 plus root 3, this does not equal root 5. We can't join it together like that, and yet in exams we see students doing this all the time. So you need to understand this a bit like algebra. Just as with A plus B, we can't somehow join that together, so with root 2 and root 3, any surd that won't simplify down, and that therefore can't be joined, we just have to write it out again. We just keep this string. So we end up with these long strings of surds, which is what we saw as we were working through the problems in part A.